Most machine learning projects end as static code. You feed data into a script, it spits out a prediction, and the process stops completely. To generate actual scientific value, we need to build something completely different, a continuous reasoning system, a pipeline that ingests messy, real-world data and outputs testable, self-improving hypotheses. We are going to build this exact system to solve a specific problem, discovering which new polymers are biodegradable, using materials like polylactic acid or PLA as our starting point. This flowchart maps out the architecture of our engine. We must construct 6 discrete layers: reality, representation, computation, evaluation, discovery, and feedback. Each layer solves a specific engineering problem. If you only focus on building a prediction model, the system fails. We have to engineer all 6 layers to work together as a single continuous loop. Step 1 is the reality layer. Out in the real world, biodegradability is chaotic. It depends on how a polymer's specific molecular structure interacts with soil microbes, moisture, and time. An algorithm cannot inherently understand a piece of plastic degrading in compost. That physical process exists entirely outside of our code. This brings us to the representation layer. Here, we must translate that messy physical chemistry into structured mathematical data that a computer can process. This matrix grid shows our first method, tabular representation. We take a polymer like PLA and condense it into a tabular array, assigning 1s and 0s to specific features, like ester bonds, and numerical values for properties like crystallinity. But a table misses how these traits interact. Our second method expands into a node and edge graph map. We link a central node for PLA directly to the specific environments it was tested in, like compost, and the physical bonds it contains. By combining the strict numerical table with the relational graph, our system can finally identify complex patterns between a molecule's shape and its environment. If you map this data poorly, your system learns from garbage. A flawed representation at this stage guarantees incorrect scientific conclusions later, regardless of how clean your code is. With our data structured, we move to the computation layer. This is where we feed our graph and table into machine learning algorithms like random forest or XGBoost. These are decision tree-based models that classify data by weighing the mathematical importance of different features. This execution engine knows nothing about actual chemistry. It operates entirely by calculating complex, nonlinear patterns across the features we provided. The direct output from this computation is a specific numerical probability score, estimating how likely a given polymer is to biodegrade. But we cannot trust that score yet. This requires an evaluation layer to catch overfitting. Overfitting occurs when a model memorizes the training data instead of learning the underlying patterns, leading to false correlations. Watch what happens in this diagram when we validate our model. To test our system's accuracy, the predictive signal must actively collide against a known, ground truth dataset that the model has never seen before. When the system predicts correctly, those logic paths glow brightly and are validated. The incorrect matches wither and dim, allowing us to isolate the errors and calculate a final accuracy metric and confidence score. Without this strict evaluation layer, the system is blindly guessing. Mathematical trust is the true output of this stage. Now we reach the discovery layer. This is the pivot point where the pipeline stops analyzing existing plastics and begins projecting what could exist. This network map illustrates how hypothesis generation works. The system applies its verified logic to shoot out exploratory edges, constructing entirely new, untested combinations of polymer features. It generates hundreds of competing hypotheses simultaneously, branching out into unknown chemical structures. To make this useful, we must build a scoring system to filter these thousands of possibilities down to actionable science. We rank every new idea against strict criteria: the model's confidence score, the mathematical strength of the features, and historical evidence. The weaker branches dissolve away, leaving only the strongest predictions. The concrete output here is a ranked list identifying the top 5 most viable new polymers, ready for physical testing in a laboratory. The final step is the feedback layer, which closes the loop. When those top 5 polymers are physically tested, we take the real-world lab results and feed them directly back into our original dataset. This corrects previous errors and permanently updates the mathematical weights in our computation layer. This continuous cycle of predicting, testing, and updating is what elevates our pipeline. It turns a static prediction script into a continuously evolving scientific intelligence. We have mapped the entire continuous flow. We take chaotic reality, structure it into representations, compute the patterns, evaluate for truth, generate branching hypotheses, and close the loop with physical feedback. A system creates actual scientific value only when all 6 layers function seamlessly together to generate and refine new ideas. Your immediate next step is to download the Project 1 dataset. We will use this CSV file to begin writing the foundational Python code for Layer 1. Stop thinking like a standard coder writing isolated scripts. Start building like a scientist, an engineer